Hi, welcome to this presentation on seismic cycles within a fault network. The relative plate convergence at tectonic plate boundaries is taken up by a series of faults within a slip partition network. The termination of major strike-slip faults is often splaying into parallel structures, for example, at San Andreas Fault in Southern California, the Marlborough Fault System in New Zealand, or the North Anatolian Fault in the Aegean Sea. Here's an example for the San Andreas Fault, starting from north to south. The San Andreas Fault system is divided into the San Andreas Fault proper, the Macama Fault, and the Bartlett Spring Fault in Northern California, forming a network of 3 parallel faults. In Central California, along the Garlock Fault, there is a system of 2 parallel faults formed by the White Wall Fault and the Garlock Fault itself. And in Southern California, there is a network of 4 parallel faults formed by the Newport, Inglewood, Rose Canyon Fault, the El Senor, San Jacinto, and San Andreas faults. Further, in the Mojave Desert, the bookshelf faulting there forms parallel structures that can consist of up to 4 different faults. So understanding the interactions between parallel fault structures is important to improve assessment of seismic hazard. So we are interested in modeling this kind of fault interactions during seismic cycles, but simulating rupture dynamics on finite faults is already quite challenging, so incorporating other faults is even more so. So seismic cycle simulations can be accomplished by various numerical methods, finite element, finite difference. But one of the most efficient method is the boundary integral method, because only the surface of the fault must be discretized numerically. The spectral boundary integral method is a subclass of the boundary integral method, where the calculations are conducted in the Fourier domain. The spectral boundary integral method exploits the efficiency of the fast Fourier transform, but is limited to planar faults. So we generalize the spectral boundary integral method to include multiple parallel faults. So we compute the evolution of stress on parallel structures due to a distribution of slip on a reference fault, and considering a constitutive relationship between traction and velocity, we can compute the evolution of slip on a fault in some areas and consider the velocity fix in areas subject to boundary conditions. So the method allows us to simulate seismic cycles in parallel faults or stepovers. So we derived a closed form expression for the elastostatic stress transfer among faults. You can see that the 3 different components of traction on a fault perpendicular to the x3 axis depends on the wave numbers in the fault parallel direction and on the spatial coordinates in the fault perpendicular direction. So this allows us to evaluate Coulomb stress transfer during quasi-dynamic seismic cycle simulations. Well, this is an example of what these solutions look like for the case of uniform slip in a square on a reference fault. So that's the displacement field that it produces in the 2 different fault parallel directions and in fault perpendicular direction. And these are the distribution of stresses caused by this slip distribution. So there are some caveats of using the spectral method. First, the discrete Fourier transform introduces periodicity of the stress field that is not always desirable. And second, the mean stress is not defined in the Fourier domain without additional information. So we can evaluate the differences that these characteristics introduce by comparing the space domain and the Fourier domain solutions. So this is the case again for a uniform slip. And this is the different stress components that it creates. And these are the residuals with the space domain solution. And as expected, large residuals accumulate near the boundaries of the domain because of periodicity, but a large mean difference also occurs throughout the domain due to differences in the mean stress between these two solutions. So the spectral boundary integral method introduces small differences to the space domain solution of the order of 1 to 5% in all practical cases. So we start by illustrating the spectral boundary integral method in the case of complex parameter regimes of seismic cycles for a single fault. And so to simulate seismic cycles, we use a physics-based constitutive law where the velocity of slip is a very highly sensitive function of stress modulated by the state of the system, which has its own evolution law. And the complexity of the seismic cycle is controlled by several non-dimensional parameters, including the Dietrich-Renner-Rice number, which is the ratio of the size of the seismogenic zone to a characteristic nucleation size. Other non-dimensional numbers include the RB number, which is a ratio of power law exponents, and the reference friction coefficient mu naught. Interestingly, as this non-dimensional parameter RU increases, the seismic cycle becomes increasingly complex. And here we show an example for the RU number of 266, which shows a aperiodic cycle of small and large ruptures that are sometimes pulse-like, sometimes crack-like ruptures, always followed by aftershocks. And that gives rise to a power law distribution of earthquake sizes. Another case of interest is the so-called seismogenic slow slip events. So slow slip events occur for a wide range of parameters in the rate and state friction framework. For example, aseismic slow slip events occur for an RU number of about 1. However, seismogenic slow slip events occur for large RU numbers in the case of a very small nucleation size, as long as the other parameters give rise to near neutral velocity weakening. And this is a case that is particularly challenging to model numerically because simulation of slow slip events require to resolve the so-called cohesion length, which in fact vanishes in conditions of near neutral velocity weakening. So the spectral boundary integral method enables these simulations in this challenging parameter regime. This is a case here where the RU number is 77, so that's a very small nucleation size compared to the velocity weakening region. However, the RB number is very small, approaching 0. And so that gives rise to these aperiodic cycles of slow slip events that are still interspersed by very small slow earthquakes that occur as the rupture fault propagate. This is illustrated in this time series of velocity, where we see a slow slip rupture that lasts several days, but still encompassing fast ruptures along the way. So we now show examples for multiple faults. In this case, 2 faults separated by a separation distance of 2.5 kilometers with an overlap of 5 kilometers. So this is an idealization of the contractional stepovers of restraining bends in push-up structures that are commonly found at segment boundaries across continental transforms. So in these simulations, we compare the seismic cycles that would occur on these faults if they were isolated and on these faults when they are coupled together. So we include different normal stresses for fault 1 and fault 2 so that they would have different recurrence times in isolation. And that avoids automatic synchronization of these ruptures. These different normal stresses give rise to a RU number of 17 for fault 1 and 21 for fault 2. And when they operate in isolation, They have distinct behavior. Fault 1 converges to a limit cycle, a period 4 limit cycle, with an alternation of large and small ruptures, and the small ruptures being sometimes slow slip events and sometimes partial fast ruptures. Fault 2 locks into a period 2 limit cycle with large and small ruptures. This is exemplified in this time series of velocity for these faults with a limit cycle of period 4 for one and period 2 for the other. However, when these faults are coupled and simply separated by a step over, the seismic cycle is much more complicated, completely aperiodic, with clustering of events, with ruptures on fault 1 sometimes following the ones on fault 2, with sometimes an inverse relationship. So we conclude by a final example that involves the finite faults, 4 finite faults in a network that represent the fault network in Southern California, consisting of the Inglewood-Rose Canyon fault, the Elsinore, San Jacinto, and San Andres fault network. They are all separated by 40 kilometers. And here we're also interested in identifying the signature of fault interactions within the network. So we consider all faults with identical frictional properties, and we compare the behavior of the seismic cycle when any one of these faults is completely isolated from the others, and their behavior when they are when they are interacting. We also consider a loading rate of 30 millimeter per year when the fault is isolated, and of 30 millimeter per year divided by 4 when they are interacting. This is to preserve the long-term relative plate motion along the plate boundary. So when any of these faults is operating in isolation, the seismic cycle is illustrated here and there. It shows a fairly periodic recurrence pattern of sometimes large ruptures of magnitude 7 and sometimes earthquake doublets of magnitude 6.5 or so that are overall separated by a recurrence time of about 80 years. However, when the 4 faults are interacting, the overall seismic pattern within the fault network exhibit much more variability, with sometimes long periods of seismic quiescence, of here 185 years, and sometimes seismic clustering of events within 20 or 10 years. However, the behavior of the seismic clustering is largely controlled by frictional properties. So this is exemplified by different simulations where we vary the nucleation size of the seismogenic zone. Changing the nucleation size, H star here, changes the RU number for these faults. So we show here different results with different RU numbers corresponding to decreasing nucleation size. But the behavior of the seismic cycle also changes as a function of RU, even for individual faults. So what we observe is that when the nucleation size is large, the interactions are weak. And so there's no strongly coupled recurrence patterns. And when the nucleation size is decreasing, we first observe clustering with a shorter recurrence times between events. And when the nucleation size decreases even more, we observe tight synchronization of seismic ruptures among these different faults. So, the seismic clustering and synchronization occurs as a function of the separation distance of faults, but also their frictional properties. So to conclude, we augmented the spectral boundary integral method to include multiple parallel faults. The method allows us to investigate the impact of geometric complexity in seismic cycles, simulations of rupture propagation across fault stepovers, and triggering among multiple parallel structures within a fault network indicate that fault interactions introduce much complexity in recurrence patterns. Accounting for geometrical complexity and interacting faults within the plate boundary increases the relevance of seismic cycle simulations for seismic hazards assessment.